Okay, you're finding the perimeter um, and the area. So let's make sense that we will do this because, well, we can find the area using. Let me show you. Look at number 23. I'm going to put this other radius from there to there, and oops, let's see. Thanks for your patience. So if we did that, if we put that radius there, and then we said, okay, um, what is this angle that we're forming in here? Well, that is the whole 360 degrees of the rotation around that central point cut into three, so each one is 120, right? So if we had all of these three radii like that, um, we would form three 120-degree angles because this is a 360-degree full rotation around there, right? So each one is 120 degrees. So, okay, so what if, let me just get that out of there. What if we then split that with an apothem? Sorry for I'm stuttering. I'm just trying to think out what I'm trying to do. So this apothem right here, okay, would split. We now have a triangle, a smaller subtriangle that looks like that, where that A is the apothem length, and we've got this 4 here as that radius length or the hypotenuse length. And we know now that we've got a 90-degree angle formed down there. Okay, so what did we know? Well, we had 120 degrees for each central angle, so if we split it in half, this will be 60, that angle 60, and we can use trigonometry to find out what this opposite side here is, because that's going to be part of the perimeter, right? We also need to find the apothem height so we can find the area. Actually, we don't even need the apothem height, to be perfectly honest, because if we have these two radii, and we know their length, they're each 4, and we know this is 120 between them, we can use that other formula that we just used in the last problems to calculate it. But let's first find x here. Well, it's a 30, 60, 90 triangle, so if the hypotenuse is 2, then A, the short leg, I'm sorry, the hypotenuse is 4, so the short leg is 2, and then this long leg, which is what x is, would be 2 root 3. Hopefully you're getting comfortable with your special triangles. And since that's the case, that's this part, uh, it's this part of the side, 1/2 of the side, right, is that 2 root 3 we just found. And so the whole side would then be, this whole thing would be 4 root 3. And once we know that, I'm going to erase what we drew here. Hopefully you can see that. Let me draw it out again here as just on this triangle, just to trace it out. What we did is we took this triangle right here, this green triangle, and we figured out that because each central angle, like between these two radii, is 120, then splitting it in half for right here is 60. We've got a 30, 60, 90 triangle, and if this side is 4, which they told us that that's 4, then we know the short apothem length right there is 2. And we then say, okay, then the long leg, which runs down here, is 2 root 3. Doubling it to get that full side is 4 root 3. So the perimeter of this whole thing would be 3 equal sides of that, or 12 root 3, and the units were meters. Now we need to calculate that because they said to the nearest tenth, which means they don't want it in radical form. So we could say, okay, let's see, the square root of 3 times 12 is approximately equal to 20.784. I'm just going to put 78 because we're going to round it. We're going to round to here. So we look here, is that 5 or higher? Yes, it is. So then we say then the perimeter is approximately equal to 20.8 and the units were meters. Okay, that's half of our answer because they also want us to find the area. Now we could use the perimeter and say the area, and might as well do this. Area is equal to 1/2 the apothem length, which is 2, times the perimeter, which is, I'm going to use the exact perimeter that we found of 12 root 3. Okay? And then notice this. The 2 times 1/2 right here is 1, and 1 times 12 root 3 then becomes 12 root 3 meters squared. That's exactly what the area is. But they don't want it exact. They want you to give it to them as decimal to the nearest tenth. So since this was exactly the same amount as we got for the perimeter, we're going to exactly get that same 20.8. This time it'll be meters squared. Excuse me, for the area. So actually, we could have used the, like I was saying, we could have used the 2 radii and that central angle as using that formula you used for the last ones. But since we already had the perimeter and we had an easy apothem length of 2, that made it easy. Just 1 second, and okay, sorry about that. A little cough. Okay, we're back. So let's take a look at this number 25 right here. And I'm going to draw, I'm going to draw this other radius here. And what we're going to do with that is we're going to figure out, well, okay, what's the central angle that we're dealing with on this? Okay, that will, of course, we'll split in half at the apothem, but what is it right now? Well, how many different sides do we have? This is an octagon, so we have 8 sides. So we're going to split these 360 degrees that will rotate around here, from here all the way around, into 8 equal parts. So let's do that. Let's split it up into 8 equal parts. Essentially what we're doing is we're saying that whole 360 rotation divided by 8, and that equals 45 degrees. So this whole thing right there is 45 degrees. So when we split it in half, you see that red dotted line? That is the apothem going down there. Okay, that's what I'm going to draw. That's what I'm going to represent here with this pink line. Okay, and then the orange line is that radius that I drew, and that becomes that triangle that we're seeing right here in the center. Okay, why am I doing this? Because we want to find out what this side length is here, x, because we need to find the perimeter, and we don't know. But we have 45 degrees for each one of those central angles, so this angle then splits in 2 to 22.5, okay, degrees. And we already know that each radius is 10 meters, so that's 10. And what can we use? Well, since we have a right angle here, we can use trigonometry, okay? And compared to that angle, which 2 sides are we dealing with? Well, we're dealing with the opposite side, which is x, and we're dealing with the hypotenuse. And what uses opposite and hypotenuse? That's sine. So we can write sine of 22.5 equals opposite x over hypotenuse 10. And then multiplying both sides by 10, we get 10 times sine of 22.5 will equal that length of x. That is essentially half of a side. Okay? So let's calculate that. Excuse me. 22.5, take the sine of that, and then multiply that by 10. And I get 3.82683, blah, blah, blah. It goes on and on and on. I'm going to keep that in my calculator as, I'll write it here as just that side is approximately equal to 3.82683 for You're going to multiply it, so I don't want to round it off too early, but we probably don't need that many digits. Now, that is, look up here on the original drawing. I'm going to put a mark here in pink. That is that much. That's that segment of the entire perimeter. And so if it goes around, there's 8 sides, and that's only half a side. We need to multiply this number by 16. So this times 16 equals a perimeter of, and I take that original number 3.82 whatever times 16, and I get, say, approximately equal to, and I get, it's weird, my pen is acting funny today, and I get 61.229, which I'm rounding it off to here, so I look here, is that 5 or higher? Yes, it is. I mean, no, it's not. Sorry, fooled you. So the perimeter is approximately equal to 61.2 meters. And now we've got one final thing to do, and I'm going to just see if I can drag this whole thing over. Whoops, nope, that didn't work. I'm just moving this over so we can finish this problem out. What you might be able to see is that sorry, this thing was glitching out. What you might be able to see is that we've got a central, well, this triangle right here, look at the original drawing. Sorry for the delay on this, but look at this original diagram. We've got these two sides, each of 10, and we know that this angle in between them is 45 because that's how it splits up when we split it 360 degrees up into 8. Okay, so what can we do there? If we wanted to find the area, we can say the area is going to be equal to 1/2 b times c times sine of a, and then just fill in those numbers. So 1/2 10 times 10, those are both from the radii, times the sine of 45 degrees. And we can calculate this, excuse me, here's my calculator. So take the sine of 45 degrees times 10 times 10 times 1/2, and we get 35.35 something. That's the area of one triangle, okay? So if I did that area, I would say, okay, that's approximately equal to, oops, approximately equal to 35.355339, whatever, I'm keeping it in my calculator, but that is only one of those 8 triangles. Look over here on the original drawing, I'm going to shade it all in. That's one of these. We need 8 total, so I need to take that amount, I need to multiply it by 8, and when I do that, I get, and because I didn't round off too early, I'm going to get the proper answer that I need to get, which is the area of the entire figure, which is going to be, what we're looking for is 282.84, approximately equal. And we are rounding off to the first place, so we look here, is that 5 or higher? No, it's not. So we get a final area approximately of 282.8. And what were the units? They were meters, so meters squared. And I'm going to box these answers out because this up here, this area, is not actually the full area. So I don't want to mark that as a final answer. That was an area of one of the triangles that we then had 8 of. We needed to take 8 of. But we do also have this as the perimeter down here. So that's the answer of that. Sorry that took a little longer than I had hoped, but you get the idea. It's mostly about you understanding it. So if you can move quickly through it,